Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the sequel lecture of Design of Tubular Connections. In this lecture number 37, we are going to take an example of design of a tubular connection. Before we move on to the example, let us revive what we have done in the previous lecture for continuation of understanding of our participants. You know, when you talk about a tubular joint, there are various parameters which will govern the design. If you look at the typical figure of a joint as shown on the screen now, this is called as a chord member and these two are the braces. Usually friends, the brace diameter is lesser than the chord diameter. Therefore, in simple terms, chord members are called the primary or the main members and brace members are called the secondary members in the design. So, the diameter and thickness of the chord are usually larger than that of the braces. Therefore, we maintain a ratio between these two for our purposes. In the previous lecture, you would have seen the empirical equations circumscribe about beta and gamma, which you must have noticed. Okay? These are nothing but the ratio of the diameter and the chord slenderness. as you see on the screen, which is already discussed in the last lecture itself. Furthermore, friends, the gap, then the angle, these are all very important parameters, and they all have ranges of application of these equations, because these equations given by the codes are based on parametric studies. They are empirical equations, therefore, there are some experimental inputs gone into preparing these equations under certain range of validity. So, they have got to be maintained. Of course, you will notice that the validity is so wider that we can fit in our all practical fabrication problems into this range, but however, one has got to be very clear that they are all empirical and there can be variations in these parameters when you compare these equations from one code to another design code. So, there are no comparison between apple and oranges, but however, the concept of design remains similar. So, we have already seen in the last lecture the failure modes, the failure types, based on which convention these equations are prepared. Continuing further, now we will talk about something called a chord factor. Which is addressed as QF. Chord factor actually accounts for presence of nominal loads on the chord where the braces are connected. The average load on the chord, the average value of bending moment acting on either side of the brace intersection should be used for the calculations. Okay, that is very important. The average load acting on the chord and the average bending moment acting on either side of the braces brace intersections should be used for calculation. Okay. The tensile axial load and in plane bending moment produces compression at the foot of the joint. That is another very important aspect which I want you to understand. The tensile axial load and in plane bending moment produces compression on the foot of the joint and they are considered as positive in computing the chord load factor. It is generally influenced by the yield capacity of the chord and the resultant moment acting on the chord due to both in plane and out of plane bending stresses caused by the braces. Okay? Let us now write the governing equation for finding out the chord load factor QF, which is given as 1 plus C1 factor of safety PC by Py minus C2 factor of safety moment in plane bending by MP minus C3 times of PC by Py into factor of safety the whole square plus FOS M in plane bending by MP whole square. So, this is the chord load factor as you see on the screen. Now, in this equation, the factor of safety represented as FOS is taken as 1.2 for the design. PC is the nominal axial load, Py and MP are the yield axial capacity, and plastic moment capacity. Of the cord. In this equation, if you see, we are looking at the ratio, right? PC by Py. PC is the nominal load, Py is the capacity. So, we are looking at the ratio. Obviously, this is the load, this is the capacity. Obviously, this number will be lesser than 1, right? The load will be lesser than the capacity and so on. We already seen that in the previous ones. Now, the constants C1, C2, C3 are also based on the experiments. The constants C2, C3 are recommended based on experiments conducted on full scale models of these kind of joints. So, now let us see what the code advises for these constants. Let us say joint type and let us say C1, C2, C3. Look at the joint type of K joint under brace axial load. C1 is taken as 0.2, C2 is also 0.2 and C3 is 0.3. If you look at T and Y joints under brace axial load, then this number is 0.3, whereas C2 is 0 and C3 is 0.8. If you look at X joint under brace axial load, and we also put one more condition, beta is less than or equal to 0.9. This should be satisfied for the X joint. So, C1 is given as for that condition as 0.2, C2 is 0 and C3 is 0.5. Now, friends, look at these equations to obtain the chord load factor, which is QF. We need to know C1, C2, C3, we have it here for different connections. We need to also have the factor of safety to be used, we have it here. We need to also know PC, Py, M and MP, we have it here. PC, Py are nominal and yield capacity of the material, nominal load and yield capacity. MP is the plastic moment capacity and M is the in plane bending coming from the system. Okay. So, this equation is now clear to be applied for an example problem to calculate. Okay. In continuation to this, if I have beta equals 1.0, then C1 becomes minus 0.2 and of course, this remains 0, this is reduced to 0. Suppose if you have, these are all axial loads, brace under axial loads. Suppose if you have brace moment, if brace is under moment loading, then for all joints C1 is 0.2 and C2 is 0 and C3 is 0.4. This is true for all joints. And as I said, these joints can have intersections in different planes and they can be causing in plane and outer plane bending. Therefore, we must also have a joint interaction equation. So, each joint must be checked for its structural fit by a unity check. So, the governing equation to do this is like this: P by PA mod value plus M by MA square of in plane bending plus M by MA mod value of out of plane bending should be less than or equal to 1. Okay. In this equation, P and M are actual forces and actual moment acting on the joint. Okay. The allowable capacity of the brace and the bending capacity, the allowable axial capacity and the allowable bending capacity of the brace, this is of the brace, okay, this is of the brace, are given as MA and PA. Let us write it like this. It should be PA and MA respectively. Okay. So, PA indicates allowable axial capacity, MA indicates allowable bending capacity of the brace for in plane and out of plane. Of course, P and M indicates the actual force and actual moment acting on the joint. Okay. Now, the question comes, how will you compute this allowable bending capacity? Actual is known to us, but how will you compute the allowable? So, the allowable axial capacity of the brace is given by QU, QF, which I already saw, FY C T square by factor of safety times of sin theta. MA, which is the allowable moment capacity of the brace, is given by QU and QF. We already calculated FYC T square D by factor of safety of sin theta. The factor of safety here in these two equations, that is this one and this one, these two are taken as 1.6 FYC is taken as yield strength in the cord or yield stress of the cord. Remember, these are all capacity of the brace, right. of the chord. We already said this will be about 80% of the tensile stress. I will write it separately on the next page. I will rub it. I will rub this. Next page. FYC is the yield strength of the chord. Which is taken as 80% of tensile strength. Okay. So, in this equation we know all of them. Now friends, with the given information, let us try to do a problem illustrating this example. Okay. Let us take a problem. So, the problem definition is like this. A K joint with a chord and braces are shown. Let us draw a K joint. So, this is the chord having some thickness. It is connected to, let us say the CG of the chord is here, to a brace this is at an angle of 45 degrees and this is of diameter 508 by 15.88 thickness. I have one more brace which is connected here. This is connected 30 degrees and this is diameter 406 and thickness is 12.7. Okay, we have a chord which is diameter 762 and thickness 19. This is the connection given to us. Now, we say the connection is under action of axial, in plane and out of plane bending. We can neglect the stresses in the chord member. We will use API code, API RP 2E. We will take Fi as 345 megapascal. Let us say the gap G is 50 mm. Okay. Let us assess this connection based on the API code. Let us do this problem. Let us say the first step is the geometric data. Let us say brace 1. The diameter D1 is 508. Okay, it's 508. Thickness D1 is 15.88. Angle theta 1 is 45 degrees. Axial load P1 is 900 kilonewton. And in plane on 1 in plane moment is 220 kilonewton meter, and for member 1 the out of plane bending moment is 110 kilonewton meter. This data are given. Okay. Let us see for brace 2 what happens. Brace 2 carries this data. The diameter D2 is 406 mm, T2 is 12.7 mm, angle theta 2 is 30 degrees, axial load P2 is 800 kilonewton and M2 in plane bending moment is 150 kilonewton meter and M2 out of plane bending moment is 100 kilonewton meter. Okay. Let us see what happens to the cord. This is about the brace. Okay. This is about the brace. Let us see what has happened to the cord which is connecting these two. Cord diameter capital D is 762 mm and capital T is 19 mm. This is given, right. Now, let us work out the solution. First, let us work out the joint geometric properties. Okay. So, we know the gap G is 50 mm. Let us work out beta 1. Beta 1 is D1 by D, which is 508 by 762, which is 0.667. Let us also work out beta 2, second brace D2 by D, which is 406 by 762, which is 0.533. Let us work out gamma, the chord parameter, which is 762 by 2 into 19, which comes to 20.053. Let us also work out G by D, the gap parameter, which is 50 by 762, which is 0.066. Let us now work out the gap factor. Or K joint. Okay, we already have this equation. I would request you to refer to the equation. I am writing it here for our understanding. So, QG is given as 1 plus 0.2, 1 minus 2.8 G by D Q for G by D greater than 0.05, 1.0. This is QG. Okay. For G by D greater than 0.05, because you know G by D what we have here is greater. So, we know we can calculate this QG as 1 plus 0.2 times of 1 minus 2.8 times of 0.066 Q. We get this value as 1.199. It should be greater than 1.0, so it is okay. Okay, that is the condition. Let us do this for brace 1 now. Let us take brace 1. Let us work out QU. Please refer to the equation, friends. It is given as 16 plus 1.2 gamma beta of power 1.2 into QG. Let us substitute this. 16 plus 1.2 into 20.053, okay, into 667 to the power 1.2 of 1.199. I get this value as 29.5. QU should be less than 40 beta 1.2 Qg. That is a limit. Let us check that. It should be less than 40 times of 0.667 1.2 power into 1.199. This is 29.5. So, we will now limit Qu of brace 1 to 29.5, okay, not this value. We will take this value, that is for brace 1. Now, let us compute the allowable axial load. The allowable axial load PA is going to be Qu to F Fyc t square by factor of safety of sin theta. So, we will take Qf, the chord factor as 1.0 in this problem. So, PA now becomes 29.5 into 1.0 into 0.8 of yield, that is my chord strength, and 19 square thickness of the chord, 1.6 is the factor of safety, and the angle of inclination is 45 degrees. I get this value as 2598.3 kilonewtons. Let us try to find out Qu for in plane bending, which is given as phi plus 0.7 gamma beta 1.2. I substitute this, which is going to be phi plus 0.7 into 20.053 times of 0.667 of 1.2 power, which gives me 11.709. That is my Qu in plane bending. Let us compute Qu out of plane bending, which is going to be 2.5 plus 4.5 plus 0.2 gamma of beta 2.6. Let us substitute this. 2.5 plus 4.5 plus 0.2 into 20.053 of 0.667 to the power 2.6. I get this value as 5.47. Now, let me compute the allowable bending stress, M allowable in plane bending, okay, which is given as Qu in plane bending of Qf Fyc t square d by Fos sin theta. Okay. So, I get this value as 11.709 into 1 is my chord factor into 0.8 times of 345 is my yield strength of the chord, 19 is the thickness of the chord, and diameter of the brace is 508, 1.6 factor of safety, and sin 45 is the angle. I get this value as 523.91 kilonewton meter. Okay. Further, I will try to work out M allowable out of plane bending. The equation is Qu out of plane bending Qf Fyc t square d by factor of safety sin theta. Let us substitute this. 5.47 is my out of plane bending value, chord factor is 1.0, 0.8 of 345 is my yield strength, 19 is the thickness of the chord, diameter of the brace is 508 and factor of safety is 1.6, sin 45 is the angle. I get this value as 244.75 kilonewton meter. Now I perform unity check. So, unity check if I do, it is given as P by PA absolute plus M by MA square of in plane bending plus M by MA of out of plane bending mod value. Let us check how much this value coming to be. So, 900 by 2598.3, that is axial. In plane is 220 by 523.91 square, that is in plane, and out of plane is 110 by 244.75 is OPB. I get this value as 0.98, so I can say the connection is safe with brace 1 and the cord. Okay, friends. Similarly, I would request you to do this for brace 2 as an exercise. Please do this as a homework for you. I will give you the values, okay, for your check. So, QU is 22.555, which cannot be more than 22.54. So, we take this value as my QU, okay. Then PA is coming to be 2807.2 kilonewton and QU in plane bending is coming to be 8.947. QU for out of plane bending is coming to be 4.157. I substitute this and get the allowable moment in plane bending as 452.41 kilonewton meter. I get allowable out of plane bending as 210.2 kilonewton meter. Now I perform unity check. Then I say P by PA mod value plus MA M by MA square of in plane bending plus 100 by 210.2 out of plane bending. If I do this, it becomes 0.87. This is also safe. So, friends, in this lecture, as a summary, we learned the design of tubular connection. We illustrated an example problem to compute or to assess the connection carefully. We found that the connection is safe, which is a cord connected by a brace of 45 degree and 30 degree. So, similarly friends, one can practice more example problems in reality and try to see how one can use these equations for understanding the design of tubular connections. Hope you understood the lecture, and please verify the substitution and the calculated values for their correctness. I have done my best to see that there are no errors, but still I will not claim it is error free. You please check it. If you have find anything different, please let us know. Thank you very much. Namaste.